Evening. I'm Spot On Weather Meteorologist Matthew Euler. Welcome to my latest training video. And in tonight's video, we're going to take a look at pressure as well as temperature advection. Now, I'm going to break this training video down into two specific parts for this topic because I just took a look at it beforehand and I'm trying to limit the amount of time that I cover some of these training topics. And if I took all of this whole section into one part, it probably would go over longer than I would really like to present. So we'll break this down into two parts. So let's begin this particular training topic this evening. Here is the overview. This is going to be the entire overview of the training here, this training video. Again, it'll be a part one, which you see here. Tonight we'll cover pressure changes aloft as well as surface pressure changes. That'll be our first part tonight. And then the second part will be the temperature advection part as well as measuring pressure. And so it's going to be a really interesting topic here. I really love this topic, by the way, because this really explains the why behind the what of weather. So let's go ahead and start with a discussion on cold air and troughs. Now, one thing we've kind of talked about and alluded to in the previous training videos that I produced, cold air is denser, heavier than warm air. If we compare two columns right down here in the bottom right, we compare one column of cold air, represented by this blue block, to a column of warm air, represented by this yellow block. And we can clearly see the height of these two columns of air is different. If we were to look at specifically, if we were to look at the 850 millibar constant pressure surface, right, how would these blocks of air change? Well, the column of colder air, this blue block, is going to be much shorter compared to the column of warmer air. And by the way, the tops of these columns represent the 850 millibar pressure level, that constant pressure surface. So you can clearly see that with a column of colder air, it would take a shorter column with this colder air to exert the same surface pressure as it would with a taller column of warm air. Okay, so the surface pressure in both cases, both columns, is 1020 millibars. But with the colder column of air, it's going to be shorter because colder air is denser and it's more compact. So there's going to be less vertical distance for a cold air column, but it's still going to exert that 1020 millibar surface pressure. And then the warm air is going to basically be taller. And it's going to, exert the same 1020 millibar pressure surface, but it's going to take a much greater vertical volume to produce that. So with cold air in general, cold column or cold air is associated with low heights aloft. And that is again because the atmosphere, what we see is we have colder temperatures throughout a vertical column of air, which means that those thicknesses or those heights are going to be much more compact. You're going to have lower heights with colder air, lower values of those heights. If you were to take off in an airplane, for example, under a cold column of air, you would reach that constant pressure value of 850 millibars a lot sooner than if you were to ascend or rise in the warmer column of air. Now, atmospheric pressure does decrease or drops more rapidly as well when you ascend into the colder air column. Okay? And here's another great example to show you. I'll go back to my laser pointer here to really point out some key parts of this particular graphic. We're going to compare colder air, which is to the east. Okay? So we have colder air over in this location where my cursor is, to the east. We have warmer air to the west. Right? And notice this blue slice here. This represents your 500 millibar constant pressure surface. And notice how this constant pressure surface, the 500 millibar constant pressure surface, slopes. It slopes downward into colder air. So basically your 500 millibar constant pressure surface is going to be lower in the colder air, right? But as we go back toward the left portion, upper left portion of this diagram, we're getting into that warmer air. And notice how this 500 millibar constant pressure surface rises. And it's going to be associated with these higher heights. So in general, the air in the east is cold compared to the west, and the 500 millibar constant pressure surface is going to go through this 5,400 meter area. It's going to go through the 5,460 meter area, all the way up to that 5,520 meter area. So what we're saying is the height in the warm air is 5,520 meters, while the height in the cold air is below 5,400 meters. Okay? And in a lot of cases in upper air charts, we will look at decameters. And really, to convert from meters to decameters, you just take the last zero off these numbers. So 5,520 meters is 552 decameters. 5,460 meters, remove that last zero, it's 546 decameters. And then 5,400 meters would be 540 decameters. So again, we're comparing the vertical profile of cold air column versus a warm air column, and your heights are much higher in a warm air column. To really make sure your understanding of this concept, here are some solid black lines. Now, each one of these lines represents a constant height value, okay? So we're looking at these constant height values, okay? So everywhere along this solid black line is 5,400 meters, or 540 decameters if we drop that last zero. Everywhere along this solid black line, the middle line here, would represent 5,460 meters, and we drop that last zero off, that'd be 546 decameters. And then this bottom last line here, solid black line, everywhere along it, the constant pressure surface is at 5,520 meters. Right, take that zero off, we get 552 decameters. So these are height contour lines, and one thing you want to realize here is we have colder air in the upper right-hand portion. We have lower heights associated with the colder air here. So our heights around this location where the colder air exists would be around 540 decameters. If we were to point out this particular area where the warmer air to the left, upper left here portion of this diagram, we have warmer air, so we have higher heights. So we may be around 5,520 meters at this location, or 552 decameters. So just keep that in mind. We look at these upper level constant pressure charts to determine where these heights are, and the lower the height, the colder the temperature, and the higher the height, the warmer the temperature. All right, so with troughs in general, what exactly is this trough over here to the right? It's an elongated area of low pressure. The trough characteristics, it's associated with that cold air aloft. That constant pressure surface is going to be lower, as we already discussed. The winds are going to blow cyclonically or counterclockwise around a trough, and it's usually associated with surface low pressure. Troughs in the up and middle levels of the atmosphere approaching an area, they're generally going to stack down towards a surface low pressure center, and they're going to be connected to that low pressure at the surface, that storm system at the surface. So just a couple examples here on the right before we move on. You notice how in the ridges here, let me go ahead and draw this out for you, or just highlight some key points. Okay, so this area here is known as a ridge axis, the sawtooth line here. You notice how that ridge takes on more of an upside down U shape. And beneath this ridge, you have warmer air, okay? So you would have higher heights or higher constant pressure surfaces associated with this ridge in the upper levels of the atmosphere. Meanwhile, a trough is marked by this solid dark line here, and it's representative of this U-shaped bending of these height values, or these height contour lines. And notice back in the cold air, in association with the trough, you have lower values for the heights, lower heights, right? So just want to point out those key features. Now these troughs and these ridges, they generally are going to go from the west towards the east in the mid-latitudes. Whether we're in the United States or Europe, these things are going to zip along in the mid-levels of the atmosphere, typically at 700 millibars, which is 10,000 feet above the surface, as well as 18,000 feet or 500 millibars. So 700 and 500 millibars, these upper air fluctuations in heights are going to occur, and they're going to have major implications on our surface weather where we live here. Cold airs and troughs with migratory baroclinic low pressure systems. A trough aloft is a definite integral part of the surface low. Think about the chimney effect, which I've covered extensively in previous training videos here on the Spot on Weather YouTube channel. But the chimney effect, we have upper level divergence, which initiates upward vertical motions. And that evacuation of mass, that divergence aloft is from a column of air, is what creates these surface low pressure systems. Let me draw this out now. All right, so let's say this is the surface. And let's say at 500 millibars, 18,000 feet, we have this U-shaped pattern, which represents my trough. So here's my trough axis. The trough axis really is going to be the lowest point, the deepest, basically the lowest bending of these height contours. That's going to represent your trough axis, okay? Now, what's going on? Now, so let's say this is at 500 millibars, okay? So this is 500 millibars aloft. All right, 500 millibars. Okay. We have this upper level trough, and it's going to be generally moving in the westerly wind belts from west to east. All right. Now here at the surface, we're going to initiate an area of low pressure at the surface, and that's going to result usually in more stormy conditions. And so in order to get a low pressure here at the surface, that is a low, believe it or not, everybody, okay? Bear with me on my drawings. I know it's not the best. Usually out ahead of this trough axis at 500 millibars, this area is going to be favored for upward vertical motion and upper level divergence. Remember what we said, upper level divergence is a spreading apart of air. Now imagine if this upper level trough here begins to interact, it connects down to the surface, we get an area of low pressure that develops. And so out ahead of the trough axis here at 500 millibars, you're going to have upper level divergence. I'll just label it as D, I, and B. Now, we're removing mass aloft up here with this upper level divergence. So, as a result, with the surface low pressure, the air is going to be rising. This divergence is being removed aloft. We're then going to have surface low level convergence coming in towards the center of low pressure. And then the air is going to continue to rise in the vertical. And it's going to basically, if this divergent area in the upper levels at 500 millibars is stronger or exceeds that of the low level convergence down here at the surface, then we'll continue to see a strengthening of this storm system, or this what we call deepening of the low pressure system at the surface. But this is the chimney effect. We talked about the chimney effect as being upper level divergence, all right, aloft, over low level convergence at the surface. Results in upward vertical motion. That's a chimney effect. So with cold air and troughs, out ahead of the trough axis, or troughs in general, downwind or downstream of it, you're going to have divergence, which reports surface low pressure development. And here it is drawn out for you again. I mean, I just drew it on the last slide to show you, but this greenish area, oval area here, represents the development of surface low pressure, and that's the letter L here. And we see that green oval shape, which represents upper level divergence. And you notice where that trough axis is at. It's back here. So out ahead of these shortwave trough axes, you have upper level divergence, you have rising upward vertical motion. Usually that's going to lead to clouds and some sort of precipitation, right? And this shows you on the bottom again of the chimney effect how we have upper level divergence spreading apart of the winds aloft. That will then cause surface pressure falls here at the surface. And that's going to result again in the upward vertical motion of air. Warm air and ridges, on the other hand, let's talk about that for a minute. Now, warm air is less dense and associated with higher heights aloft. It makes a lot of sense, right? If you have warmer air, you're generally going to have, whoa, I didn't mean to do that, apologize. Let's fix this here. So with warm air, you're generally going to have higher heights or higher constant pressure surfaces. Why is that? Because warm air is less dense than cold air. It likes to expand. All right, so warm air here at the low levels of the atmosphere, let's just say this is WA, warm. We'll just say WA represents warm. So you have warmer air, and it's going to result in these higher heights in the upper parts of the atmosphere because of the expansive nature of warm air. All right, so you notice how it's like a big dome here? that represents your higher heights up here. So if warm air is ascending or rising, the air is rising in the warm air. Okay, that's why I drew this vertical arrow pointing upward. You would reach a prescribed pressure value at a much higher level if you were like to ascend in warm air. It would take you longer to reach that prescribed constant pressure surface as compared with cold air. You'd have to go higher up. With warm airs and ridges now, upper level ridge characteristics, let's break this down. They're associated, upper level ridges in general are associated with warmer air aloft. So again, that's that constant pressure surface at a higher elevation or altitude above the ground. The winds are going to blow anticyclonically, or kind of like the hands of the clock on a wall around. They're going to blow anticyclonically or clockwise around the ridge, and usually associated with surface high pressure are these upper level ridges. And upper level ridges resemble mountains or hills of air moving through the atmosphere. So now let's examine with this diagram on the left. All right, notice a couple things here. The ridge axis is this black solid sawtooth line. See that? And the ridge axis is going to be the point at which you have your highest pressures or your highest heights or highest constant pressure surfaces reached when you have a ridge axis, okay? Notice the shape again, it's upside down U shape. Notice that warm air is going to be directly beneath that ridge. And notice one other thing. Look at how your heights tend to get higher with height. All right, so in general, this is a ridge. So with warm air and ridges, the migratory baroclinic upper level ridges are associated with surface high pressure systems that move in and out of an area. With a migratory baroclinic high pressure system, a ridge aloft is going to support that surface high. In this case, we have the damper effect where we get upper level convergence or the coming together of the winds aloft above the ground, meeting, and then that air sinks. So we get downward vertical air motion now. When air sinks, from my previous training, we learned that as air sinks, it dries out and it warms, adiabatically warms. All right. So sinking air motion, we're not going to have any form of clouds with surface high pressures. Typically, we have very nice weather when you see those blue H's on the surface weather map. So we have downward vertical motions, divergence at the surface, upper level convergence above that. That's the damper effect. It's because with the upper level convergence aloft, we have addition of mass. So excess of mass is going to have to go downward in the atmosphere. And that also creates these surface high pressure systems. The air pressure is going to rise to the surface with a damper effect. I'm going to draw this out. Okay, let me do this real quick. So with the damper effect, remember that as we have upper level convergence, or these two air streams, these winds are meeting like this. Where they meet right here, right, because they meet head on like this, the air is going to be forced to go downward in the atmosphere. This is the surface here, down here. I'm going to just make an S. I'll make the surface an S, and I'll make the upper levels of the atmosphere a U. So we have the air coming together, upper level converging air. Then that's going to result in the sinking downward vertical air motion in the atmosphere. And as this downward vertical air hits the surface, it's going to spread out, resulting in low level divergence, or the spreading out of this air. Okay. Now, the stronger surface high pressure systems, you can understand why surface pressure rises in this case, because the air is sinking and it's pressing more weight at this point on the surface, right? So your barometer needle is going to read higher. And just one more thing to keep in mind is that if this upper level convergence exceeds the low level divergence, the surface high pressure system will continue to get stronger. All right, so in general, warm air ridges, upper level convergence downstream of a ridge initiates downward vertical motions and supports surface high pressure system development. Here are the graphics on the left. Okay, so you notice the converging of air here, forcing the air to sink in the vertical. As air sinks, it warms and dries out, so we have no clouds. And as this air works its way down in downward vertical motion, it's going to add more surface pressure. Here at the surface, more pressure exerted on the surface there, that's going to result in this H, or high pressure, in fair weather. Usually you get pressure rises with this kind of situation. Notice with the upper level ridge, okay, this is your ridge axis here, and notice where surface high pressures generally like to form in relation to these upper air ridges. They generally like to form downstream represented by this green oval color here, and the H is your surface high pressure. So you kind of see where the upper level convergence is most favored. It's basically to the right or downstream of this ridge axis. So with surface pressure changes in general, just keep in mind, we talked about the pressure gradient force in a previous video, training video, but the pressure gradient and the pressure, just talk about pressure gradient first, then we'll get to the force here at the last bullet. But pressure gradient refers basically to the amount of pressure change that we see over a specific distance in the horizontal. So let's say you take a trip from Washington, D.C. to Indianapolis. All right, if you were to have a barometric pressure reading in your car, so you have a barometer in your car, as you start your trip in Washington, you note what the pressure reading is on your barometer, and as you continue to move westward towards Indianapolis, you notice how the pressure changes on your road trip. This is an example of pressure gradient, changing pressure over a horizontal distance. Now, when there is a difference in air pressure, there's going to be a force acting on the air, and this is called the pressure gradient force. And you're most likely going to get that pressure difference. Like I said, we're using the road trip from Washington to Indianapolis as an example. Your barometric pressure most likely will not be the same when you reach Indianapolis, your destination, as it was when you left Washington, D.C. It's going to be different. And that's going to result in this pressure gradient force to develop. Now, this pressure gradient force, its initial PGF, it causes the wind to blow from higher toward lower pressure. If we were to look at pressure overall versus elevation, okay, pressure is generally going to decrease with height or with altitude. For example, if you were at a city at sea level, such as LA, let's say you're here, around LA. Let's just call this area LA. Let's say the surface pressure reading on your barometer in LA at sea level is 1,000 millibars. But if you climbed up, let's call this Mount Whitney here. If you were to climb up Mount Whitney, the pressure may only be 600 millibars up at 14,000 feet at the peak of Mount Whitney. So you can definitely see, and we're talking about the same air mass here, but a change in elevation can definitely be responsible for a change in the air pressure. The higher you go in elevation, the lower the air pressure. And with temperature and pressure now, when you get decreasing or colder temperatures, they're going to increase your density, and near the surface specifically, this is going to result in higher pressure. Some of the strongest higher barometric pressure readings have occurred in the wintertime over Siberia in association with the Siberian high. I mean, there have been cases where surface pressure has reached 1060 millibars in some cases. Now, just for reference point, 1013 millibars is average sea level pressure. So you can really see how dense and cold that air must have been at 1060 millibars. Most of the summer, by the way, because we have warmer, less dense air masses in place, most of the summer is going to be dominated by high pressure. But because that lighter, warmer air is in place, surface pressure is usually going to never get higher than about 1030 millibars. So there's a considerable difference in the barometric pressure readings between the summer season with warmer, moist air in place versus the winter season with cold and dry air in place. Now, temperatures can also change over the course of a day, from sunrise through the nighttime after sunset. When the sun's high in the sky, for example, you got the most intense heating of the day, surface pressure can drop as much as 2 millibars. And at night, after the sun goes down, the temps cool, the pressure can then rise 2 millibars prior to sunrise. So you can have this diurnal pressure change of 2 millibars on average based on the heating of the day and the cooling of the day. Okay, this wraps up part 1 of this exciting training video. This is pressure and temperature advection. In the next part 2, we are really going to get into the meat and potatoes of meteorology and why, what happens to the ridges and troughs, with the intensity of both. And we're going to tie in these temperature changes, these temperature advection patterns of cold and warm advection. And we're going to see how cold and warm advection really impacts ridges and how it impacts troughs, how it impacts their speed of movement as well. And then to end this training video, in part 2, we'll talk about different types of pressure readings: station pressure, sea level pressure, special types of barometric readings for pilots, where they do altimeter readings, and we'll talk a lot about that. So really appreciate everyone subscribing to the Spot and Weather YouTube channel. We'll continue our training video series with part 2 next, pressure and temperature advection. Got much more beyond that you're really going to love. And again, hope you're learning a lot over the summer about basic weather. And until next time, take care and God bless everyone.